X. It means the field is directed down into the page or into the screen. From Faraday's law, EMF is equal to N delta phi over delta T. We don't have any terms, so EMF is equal to delta phi over delta T. So EMF is equal to delta phi, yes, is equal to magnetic flux density times the change in the area of the linked flux lines over delta T. So delta phi, which is equal to B delta A over delta T. As I said, delta A equals delta X times L. So EMF equals delta X times LB over delta T. Delta X is distance. Distance over time gives the velocity. So we can say EMF is equal to negative sign BLV, okay, where in this particular case the wire moves perpendicular to the field. Your attention, B is the magnetic flux density, L is the length of the wire, V is the velocity with which the wire is moved. In general, EMF is equal to negative BLV sine theta, where theta is the angle between the direction of motion of the wire and the magnetic field. And now, talking about the EMF induced in a wire moving in a magnetic field, the factors affecting the size of this EMF. First of all, magnetic flux density of the field. So density of the field is the first factor affecting the EMF induced in a wire. Length of the wire, okay, and velocity of the wire. And finally, sine the angle between the direction of motion of the wire and the magnetic field. All factors, are taken from the expression EMF induced is equal to BLV sine theta. And now let's try to solve some problems. First problem, a coil of area 8 centimeter squared. So area of the coil is 8 centimeter squared. And 300 turns, number of turns on the coil is 300, is placed at right angles to a magnetic field of density 5 times 10 power negative 3 Tesla. We want you to calculate the average EMF induced in the coil, okay? In the following cases, when the coil is rotated through an angle 90 in 1 second, okay, when the coil is reversed in 0.1 second, when the magnetic flux density through the coil is increased to be 9 times 10 power negative 3, and instead of being 5 times 10 power negative 3, we'll increase it to be 9 in a time of 0.1 second. And finally, when the coil is removed from the field in a time of 0.1 second. We'll take it one by one. The first case, when the coil is rotated through an angle 90. Okay, EMF is given from Faraday's law. EMF is equal to N delta phi magnetic over delta T. Coil is rotated through an angle 90. Delta phi equals phi. So EMF equals negative sine N phi, which is equal to A, and change of the magnetic flux density over delta T. So we can say EMF induced is equal to negative 300. 300 is the number of turns. Okay. Area of the coil is 8 centimeters squared. To convert from centimeters squared into meters squared, So it is multiplied by 10 power negative 4. Okay, a change in flux is from 5 times 10 to the power of negative 3 to 0. So 0 minus 5 times 10 to the power of negative 3 over 1. This happened in a time of 1 second. Okay, so EMF is equal to 1.2 times 10 power negative 3 volt. In the second case, when the EMF, when the coil is reversed, what about the EMF when the coil is reversed? Okay, when the coil is reversed, the change in the magnetic flux, delta phi magnetic, is equal to, phi magnetic. So it is equal to 2 times A times B. We'll use the same rule. Okay, Faraday's law, EMF induced in this case will be equal to negative sign, which indicates Lenz's rule. Number of turns 300. Okay, between two brackets, 2 times 8 times 10 to the power of negative 4 times 5 times 10 to the power of negative 3, and time is given to be equal to 0.1. So EMF is equal to negative 0.024 volt. So your attention, when the coil is reversed, delta phi magnetic equals 2 phi, and phi is equal to the product of area and flux density. Okay, and what about when the magnetic flux density through the coil is increased from 5 to 9 times 10 to the power of negative 3? Once again, same formula. So EMF equals N delta phi magnetic over delta T, delta phi magnetic A delta, beta over delta T. So number of turns 300 times 8 times 10 to the power of negative 4. 8 times 10 power negative 4 is the area. B is changed from 5 to 9. So the difference, 9 times 10 power negative 3 minus 5 times 10 power negative 3 over the time. This happened in a time of 1 second. Okay, this happened in a time of 0.1 second. The EMF will be equal to, minus negative sign 9.6 times 10 to the power of negative 3 volt. And finally, when the coil is moved away from the field, using the same rule, okay, now the coil is subject to the field and is removed from it. Okay, so we've got a change of phi. So number of turns 300, area 8 times 10 power negative 4. Final flux is equal to 0, initial 5 times 10 power negative 3 over 0.1. It is equal to 0.012 volt. Another problem, a circular loop in the plane of the paper, plane of the screen, lies in a 3 Tesla magnetic field that points down into the page. The loop's diameter, it changes from 100 centimeter to 60. So the area is decreased, diameter is decreased. So we are decreasing the magnetic flux passing through the loop. So the induced current will be in the same direction. Once again, circular loop in the plane of the paper lies in a 3 Tesla magnetic field that points down into the page. The loop's diameter changes from 100 to 60 centimeter in a time of 0.5 seconds. What is the magnitude of the average EMF? What is the direction of the induced current? Magnitude is determined from the expression EMF equals negative N delta phi magnetic over delta T. So it is equal to negative n. Magnetic flux density, the change in this problem is in the area, in the diameter. So it is equal to negative nb delta A over delta T. It is equal to minus 1, 3 pi between two brackets, 0.3, yes, squared minus 0.5 squared over 0.5. Okay, the EMF is equal to 3.017, and its direction, as I said, it is clockwise. Another problem, if a coil of 150 turns is linked with a flux of 0.01 Weber. So turns number is 150, phi 0.01 Weber. When carrying a current of 10 amperes, calculate the inductance of the coil. We want coefficient of self-induction. And if the current is reversed in a time of 0.01 second, calculate the induced EMF. So talking about the inductance, EMF induced is equal to negative n delta phi magnetic over delta T, and also it is equal to negative L delta I over delta T. So we can say L is equal to n delta phi magnetic over delta T. Number of turns 150. Change in flux is 0.01 and the current is 10, so it is 0.15. H stands for Henry. So inductance equals 0.15 Henry. Okay, and what about when the current is reversed? When the current is reversed, the current is multiplied by 2. Current was given to be equal 10. So in the expression, it will be 20. L is equal to inductance 0.15. Current, as I said, 10 times 2, so it is 20 over the mentioned time. It is 0.01. So the EMF induced is 300 volt. Since EMF induced is, yes, determined from n delta phi magnetic over delta T, so this is another method to calculate the EMF induced using Faraday's law. Current is reversed, delta phi, yes, equals 2 phi. So once again, 150 times 2 times 0.01 over 0.01, the same answer, it is 300 volt. Another problem, a circular coil has 1000 turns and cross-sectional area 20 centimeter squared. So number of turns 1000, area 20 centimeter squared. It should be converted into meter squared. Yes, it is multiplied by 10 power 4, 10 power negative 4, with a current of 4 amperes. The magnetic flux density that threads the coil is 1 Tesla. With a current of 9 amperes, the magnetic flux density that threads the coil is 1.4 Tesla. Calculate the inductance of the coil. EMF induced is equal to, yes, negative n delta phi magnetic over delta T, and it is also equal to L delta I over delta. So self-inductance L is equal to n delta phi magnetic over delta I. It is equal to, yes, Na, change in magnetic flux over delta I. So it is equal to 1000 times 20 times 10 power negative 4. The flux changes from 1 to 1.4, and from 4, and the current, when the current changes from, yes, 4 to 9, and the inductance is equal to 0.16 Henry. Another problem, a direct current of 1 ampere is passed through a coil of 5,000 turns. So current intensity is equal to 1 ampere, number of turns on the coil, 5,000. Okay, and a flux of 0.1 milliweber is, yes, produced. What is the inductance of the coil? So once again, a direct current of 1 ampere is passed through a coil of 5,000 turns and produces a flux of 0.1 milliweber. What is the inductance of the coil? Also, what would be the average EMF induced in the coil if the current were interrupted in 10 to the power of -3 seconds? EMF induced is equal to negative N delta phi magnetic over delta T. It is equal to negative L delta I over delta T. So we can say inductance is equal to N delta phi magnetic over delta I. So the inductance is equal to 5,000 times 0.1 times 10 to the power of -3 over, 1. It is 0.5 Henry. EMF induced is equal to negative L delta I over delta T. Okay, so it is equal to negative 0.5 between two brackets, 0 minus 1, okay, over the time, which is 10 power -3, it is 500 volt. Another problem, a cord solenoid has 300 turns. Its length is 25 centimeter and its cross-sectional area 3 centimeter squared. Length of the solenoid 25, turns 300, area 3 centimeter squared. Calculate the inductance of the coil. Inductance is given from the expression mu A n, number of turns squared, over length. So it is equal to 4 pi times 10 to the power of -7, which is the permeability. Area is equal to 3 times 10 power -4 to change it from centimeter squared into meter squared. Turns squared will be, 90,000 turn over the length 25 centimeter. It is 25 times 10 to the power of -2. So inductance is equal to 1.357 times 10 power -4 Henry. Another problem, two coils X and Y of 1,000 turns each. So number of turns on each one of them is 1,000. They lie in parallel planes such that 80% of the flux produced by one coil, links with the other coil. If a current of 5 ampere flowing in X produces a flux of 0.5 milliweber in it, find the mutual inductance between the two coils, between X and Y. EMF induced is equal to minus N delta phi magnetic over delta T, and also equals, negative M delta I over delta T. So mutual inductance is equal to N delta phi over delta I. So it is 1,000 times 0.8 times 0.5 times 10 to the power of -3 over 5. It is 0.08 Henry. Another problem, if a coil of 150 turns is linked with a flux of 0.01 Weber when carrying a current of 10 amperes, calculate the inductance of the coil if the current is reversed in 0.1 second. Calculate the induced EMF. if a second coil of 100 turns is uniformly wound over the first, find the mutual inductance between the two coils. Inductance of a coil is given from the expression capital N delta phi over delta I. It is equal to 150 number of turns. Flux 0.01 over change in current, it is equal to 10. So inductance is equal to 0.15 Henry. Since EMF is equal to L delta I over delta T, so it is equal to 0.15 times, 20. The current is reversed, so it is multiplied by 2 over 0.1. EMF is equal to 30 volt. Inductance, denoted by M, mutual inductance, is given from the expression N delta phi over delta I. So it is equal to 100 times 0.01 over 10. It is 0.1 Henry. Another problem, a solenoid of length 10 centimeter and cross-sectional area 25 centimeter square has 400 turns. A current 4 ampere is sent into the solenoid. Permeability equals 4 pi 10 power. Permeability is equal to 4 pi times 10 to the power of negative 7 Web per ampere meter. Calculate the magnetic flux that intercepts the solenoid, the coefficient of self-induction of the solenoid. Okay, the average EMF induced in the solenoid when the current is reversed in 0.1 second. Magnetic flux density of a solenoid is given from the expression B equals permeability Ni over L. N number of turns, I current intensity through the solenoid, L is the length. So B equals 4 pi times 10 power negative 7, turns is equal to 400 times 4 over length, which is 10 centimeter, 0.1 meter. So it is equal to 0.02 Tesla. Phi is given from the expression AB. So it is 25 times 10 power negative 4 times flux, which we managed to obtain it, which is 0.02. So magnetic flux is equal to phi times 10 to the power of negative 5 Weber. And what about the EMF induced? It is equal to L delta I over delta T, and also is equal to N delta phi magnetic over delta T. So L delta I is equal to N delta phi magnetic. So self-inductance is equal to 400 times 5 times 10 power negative 5 over 4. It is 5 times 10 power negative 3 Henry. EMF induced, as I said, is equal to negative L delta I over delta T. It is equal to negative 5 times 10 power negative 3, 4 times 2, current is reversed, over 0.1, it is 0.4 volt. And it can be calculated using the rule or formula. EMF induced is equal to negative N delta phi magnetic over delta T. It is 400, 5 times 10 power negative 5 times 2, because the current is reversed. So delta phi equals 2 phi over 0.1. Once again, the same result, it is 0.4 volt. The primary coil of Ruhmkorff coil has 200 turns and is wound on a core of length 10 centimeter and diameter 3.5 centimeter. The core is made of a material of permeability. What about the permeability? It is 0.002 Web per ampere meter. The secondary coil has number of turns, which is equal to 10 to the power of 5 turn, and is wound around the primary coil. A current of 4 amperes is flowing into primary coil, interrupted in 0.01 second. Calculate the EMF induced in the secondary coil, the mutual inductance. Yes, beta is equal to mu Ni over L. It is equal to 0.002 times 200 times 4 over 0.1. It is equal to 16 Tesla. Area equals pi r squared, 22 over 7. Yes, times 1.75 times 10 to the power of negative 2 squared. Okay, so area is equal to 9.625 times 10 to the power of negative 4. EMF induced is given from expression N delta phi magnetic over delta T. It is equal to NA, change in magnetic flux density over delta T. So it is equal to, number of turns is equal to 10 power 5, 9.625 times 10 power negative 4 times 16 over 0.01. It is 1.54 times 10 to the power of 5 volt. EMF induced is equal to negative M delta I over delta T. Okay, and also equal to negative N delta phi magnetic over delta T. So M delta I is equal to N delta phi magnetic. So mutual inductance equals 10 to the power of 5 times 9.625 times 10 power negative 4 times 16 over 4. It will be 385 Henry. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you very much.